Hello, madam. Hello.
Sir, good afternoon, sir.
Good afternoon, madam.
Sir, am I audible, sir?
Audible, madam. Is my voice is audible?
Yes, sir. Yes, sir.
Yes.
You can share your screen, sir.
Share my screen. Okay. Is it
Yes, sir.
visible, madam?
Yes, sir. Visible, sir. You can put it in a full screen, sir.
Madam?
So Sir, put it in the slideshow screen, sir.
What, madam?
Slideshow. Slideshow.
Slideshow.
Yes, sir. It is. Yes, sir. It is. It's in full screen. So we will wait for 5 minutes, sir. Participants are being joined. Participants only there. We will wait for 5 minutes, sir.
Yes. Yes.
So your side, some noise is coming actually, sir.
Okay, I'll. Sound.
Shubha ma'am.
Yes, ma'am.
Shall we start, ma'am?
Yes, ma'am. Of course, ma'am. It's ready, ma'am.
Okay. Good afternoon, participants. It gives me immense pleasure to introduce guest speaker of this afternoon session, Mr. T. Alavanda, Assistant Professor, Senior Grade, KPR IET, Department of Biomedical Engineering, Coimbatore. He is doing his PhD on biomedical implant design in Anna University, Chennai. He completed his MTech Biomedical Engineering from Shastra University in 2004, BE from Anjali Ammal Mahalingam Engineering College in 2001. He is having more than 18 years of experience, and his research interests are bioimplants, embedded system, neuromorphic circuit design, analog VLSI, ISPET. He presented many research works in national and international conferences and published around 6 research papers in reputed journals. At this small intro, I have handed over this session to Mr. T. Alavanda. Welcome you, sir.
Oh, yes, madam. Good afternoon, everybody.
Good afternoon.
First of all, thank to the organizer of the PSNA College of Engineering Technology, Department of Biomedical Engineering. Today, I am going to handle on the topic of biomem sensor simulation using COMSOL multiphysics. Okay. So why I have chosen this topic? Because today there are so many handheld devices or portable devices and implantable devices are coming, which is having both electrical and mechanical and other integrated systems. Okay, so if you take any system without the sensors and actuators, we cannot full-fledged measure the corresponding output or corresponding data. So for measuring or to provide output for external device, we need MEMS sensors. So what is a MEMS? MEMS is nothing but micro electromechanical system. So micro comes the size of the system. Okay, so based on that, it is given micro, that is less than 1 to 100 micrometer, not less than. The size varies from 1 to 100 micrometer, and it consists of both electrical and mechanical integrated with multiple tasks. So it is called as micro electromechanical system that uses micro components. Another version of this micro electromechanical system is NEMS. Nowadays we are having NEMS having the nano size, nano electromechanical system, whose size varies less than 100 nanometer. Okay, so both NEMS and MEMS have its own application in biomedical. Then it is called as biomems or bionems. There are so many application available in optical field also. Then the MEMS and NEMS are called as MOEMS, micro opto electrical mechanical system, nano opto electrical mechanical system. Okay. So any thing that has size in the micro and nano is called as MEMS and NEMS. And in the field of biomems, there are variety of applications available. Without MEMS sensor, there is no device in the field of biomedical engineering. For example, when you take a glucometer, which we are using a homemade or home health instruments, home side instruments, handheld. Okay, there are so many meters which we are using nowadays in our home itself. Ordinary people is having. For example, in my home, I have BP measurement system, sugar measuring glucometer system, temperature system, and pulse oximeter. All these things which measures the saturations of the oxygen, pulse oximeter. So all the devices are having MEMS sensors. Without MEMS, we cannot measure those parameters. Biological parameters plays a vital role for treating the devices. Okay, so there are different type of sensors we can classify based on the placement. One is topical sensor, which are placed above the skin, above the body. Okay. Other set of devices, sensors, we can use it internal and external. What we can call it as like glucometer. Okay, or certain devices in autoclave, we can use certain sensors. So in vitro and in vivo for biomedical applications. Then implantable devices. For example, you measure the heart rate so that for pacemaker, it is able to generate the corresponding required number of pulses, whether it increases or decreases. So there we need a sensor to measure the pulse which is generated by a normal heart, okay, normal human heart. So implantable devices having the MEMS sensors, okay. Just a minute. So, what is the advantage of using these MEMS sensors? MEMS sensors, first of all, because of its size, it reduces the sensor size so that any number of external system can be integrated, and due to its size, it has able to produce MEMS plays a vital role in measuring the target price parameters. And similar way, instead of having a large volume of reagents, we can have a small volume of reagents to identify. One such thing, blood group identification system, portable blood group identification system, which having small amount of reagent, we can identify the blood group. Okay, that MEMS, bio-MEMS sensor plays a vital role. And this bio-MEMS sensor reduces the time. It produces immediate results with a high effective. And it also suitable for both in vitro and in vivo measurements. So these are all the advantages of the miniaturization of the sensor. So that miniaturization is provided by your micro mechanical electromechanical system MEMS sensors. Okay. Next slide. Okay. Now, what are the requirements? So we can classify the bio-MEMS into two, that is sensors and actuators. Sensors are the thing which gets input from the target, whereas actuator will produce a force from the MEMS sensor, will activate the target. Okay, the output will give output to external environment. So, what are the requirements for a MEMS sensor and actuator? The sensor should be having higher sensitivity of the target parameter, better linearity, that is crystallisis should not be that much. Then better responsivity, that is immediate response should be there. The output should be displayed. What we are getting amount of sugar within a fraction of a second, glucose availability. Dynamic range. The dynamic range is very much important because very small changes is also required that should be measured by the MEMS sensor. Very small ranges, 0.001 ranges. Changes should also be identified. That is very much important when you are using bio-MEMS sensor. The accuracy will be, dynamic range accuracy should be very high. Dynamic ranges, that is, it should measure from, for example, the glucose level from 54 to 500. That is the dynamic range, but the accuracy should be exact. Okay. Then, due to that size, the cost reduction should be there, and batch fabrication is also possible. Okay. These are all the requirements for the sensors. Similarly, actuators, the speed of response and the output which it is targeting, the output is given to the system should have low power consumption. So MEMS sensor, when you are using, definitely it uses very low consumption and reduce the cost as well as the batch production. Okay. So any system that we are designing or before coming into market, it should be modeled and it should be simulated and it should be tested. Okay. What is the need of modeling and simulation? Either it may be a MEMS or anything, it may be a circuit board or it may be a device level or it may be a system level. The first thing is direct experimentation of that physical system or physical device will be very difficult for us because we doesn't know the physical properties. And direct experimenting the system level fabrication is very difficult. Okay, so before that, we should simulate or we should model and we should test by using the softwares to reduce the errors. Okay. Then time reduction, because for example, if you have a embedded system, you are simulating your program by using the Kale software. That Kale software will tell you whether your program is having error or not. Okay, before dumping it into the chip. Suppose if you are not simulating, you are writing a program and you are dumping into that chip. If it shows error, you are not getting output. It doesn't know whether the program is having the error or the chip is having error. Okay, so you have to do multiple time programming and you have to test it. You have to dump it every time, whether it is error in the program or whether error in the chip. It doesn't know. Okay, so the time is reduced because of this modeling and simulation at any level, either at device level or up to the final system level. Okay, top-down approach or bottom-up approach for any kind of sensors or to the system. The simulation and modeling is required, which reduces the time reduction as well as the production cost or cost of manufacturing. Okay. Then it also provides the modeling and simulation will also provide accurate decision making, whether this value, this MEMS size is suitable for this system, or whether size we can increase it, or whether we can size reduce it. So we can take accurate decision by using the modeling and simulation. And it also provides you the better understanding of the device performance so that the operation of that system can be optimized. Final result, final end product result can be optimized. Okay, so any modeling and simulation will provide you the optimizing the operation of that system, better understanding of the system function. Similar way, the modeling and simulation enables the designer to investigate the behavior as well as to see the future cause and effect also. The modeling and simulation will also provide you the cause and effect. Suppose, for example, if you are using a glucose sensor, MEMS sensor, and when it is working with a normal blood, it is providing a better result. Okay, a normal person's blood, it is providing a better result. Suppose a person who is having a cancerous blood. Now, the sensor will provide you the same result or the behavior of that sensor is changing. This we doesn't know until unless or if you take a cancerous blood and test it with it, and you cannot tell that whether the value is correct or not. Okay. Now we can do a modeling and simulation for the same sensor with a cancerous blood data, and we can study the behavior, whether the behavior will be the same by using the modeling and simulation. Okay, so we may not discovered earlier, such as for example the COVID-19, which we have not seen earlier. If you want to measure the COVID-based MEMS sensor, now they are going. Certain paper have been published. I have seen IS FET, ion sensitive FET, for measuring the that is the density of or the level of COVID, whether it is a mediumly affected patient or severely affected patient. That can be identified by using a simple sample, a small sample, by using the IS FET sensor. Such paper have been discovered. Now the MEMS plays a vital role. Rather than taking the huge sample and testing, a small sample range is more than enough to test whether the target is having affected by the COVID-19 or not. Next slide. So for modeling a MEMS often requires interdisciplinary knowledge because the MEMS itself, the name itself provide you micro electromechanical system. So it is going to have integration of mechanical and electrical background. Okay. So a MEMS sensor is not only required the mechanical and electrical, but also all kind of all engineering discipline, that is physics, electronics, mechanical, electrical, chemical, everything is required. Even for example, a sensor which you can place in your room to measure how much amount of radiation is coming from your cell phone, which affects the human being. So now you need the civil engineering knowledge also, okay, for the MEMS, for simulation, for modeling, okay. So not only mechanical and electrical background, it requires all kind of knowledge for which application you are designing that MEMS sensor. Okay, depending on the application, you need other information also like thermal, optical, biological background, even all kind of civil, computer science, all the knowledge are required. So when you talk about modeling and simulation, there are two types. One is theoretical modeling and numerical modeling. Okay, so before prototyping or before getting manufacturing, this theoretical modeling or numerical modeling is very much required. When I explain any topic to the student, engineering is nothing but application of both science and mathematics. Okay. So without, if you talk about, for example, everyone will be telling, certain people will be telling this subject is theory, that subject is problematic. It is not in engineering, there is no subject is theoretical one. Even environmental science is also having some mathematical functions, which defines the physical phenomena. Okay, only we assume that this paper is theoretical, that paper is numerical, that is problematic, like that. In engineering discipline, every subject is having its own scientific concept and scientific concept related numerical equation. So, for example, when you talk about theoretical simulation means, that is, you take a Ohm's law and make an equation V equal to IR. It is a theoretical concept of simulating. A simple example. When you talk about numerical characterization, take the same Ohm law and vary with the different iterations, with the different environment. That is nothing but numerical characterization. So both theoretical and numerical characterizations are required for engineering. Before prototyping, they required both. But most of us, we are using numerical characterization when you talk about simulation system. Any kind of simulation we are doing. So many softwares available like TCAD for device modeling in electronics, Cadence. So many softwares which uses numerical characterization. So before prototyping and before manufacturing, we need to do the theoretical and numerical modeling. to reduce the manufacturing cost and time. So these numerical characterization uses the mathematical representation of the physical phenomena of the system behavior or the device behavior. Okay, this mathematical representation is described by using partial differential equations, and these partial differential equations which have some analytical solution done by your numerical tools which are necessary to stimulate. Okay, so here we are going to use numerical modeling to simulate the MEMS design, which uses most commonly most of the softwares which you are using are finite element analysis. Okay, finite element analysis is the numerical method which we are using for most of the numerical modeling of the MEMS software. So what are the key softwares which we are using for MEMS simulations? Are ANSYS, COMSOL, Sugar, Counterware, MEMS Pro, MEMS Solver, and IntelliSuits. Right? Each and every software has its own identity, because we cannot tell this is better than that, that is better than this. Each and everything plays at different level of MEMS sensor designing. Okay, ANSYS plays for analysis, linear and non-linear analysis at structural basis. Most of the ANSYS is used in mechanical people, but in biomedical also we are using, for example, heart valve modeling, and that is so many implants which we are modeling, crunches, okay, bedside systems. There are so many things which are simulating using ANSYS, which is capable of performing the linear and non-linear analysis. Counterware is another software which is used for designing the virtual fabrication. Okay, before fabrication, what is the condition, or how the after fabrication, how the system will be, how the sensor will be. That will be designed by Counterware. Device level simulation, normally we call it as TCAD for devices for designing inside a chip. If you are designing a transistor, you are having lakhs of transistor. The behavior of individual transistor, how it will be inside a chip. We use TCAD here for MEMS inside a mechanical system, how it will be behaving. That MEMS sensor will be behaving. That will be designed by Counterware. Then IntelliSuite, that gives you modeling, simulation of the MEMS sensor. The process simulation. The process simulation, normally we know that in electronics, for designing a single transistor, everyone we are teaching in LIC and VLSI, different steps involved in photolithography steps. Okay, that mask formation and the exact structure of that diffusion and ion implementation of the individual terminals, that is base, collector, as well as the emitter terminals, how we are, what is the size, and those things will be simulated or modeled in IntelliSuite. Okay. MEMS Pro, which provides system level design. Okay. System level design is very much important. It is similar to what we can call it as our embedded Keil softwares, or There are people who are using circuit level like Workbench, Arcade, SpaceSpice. Those are the system level integrity. We are not only going to have, suppose a system means it will be having all kind of components, okay, electronics, electrical, and other things. So system level design can be done using MEMS Pro, and MEMS solver is both IntelliSuite and IntelliPro. What it is designed, the same thing is done by the MEMS solver. Then Sugar is another open source software which is used for simulating MEMS sensors, nodal analysis technique. Okay, nodal analysis techniques we are using in circuit theory and other thing like that. In mesh also we are having nodal. That here we have mesh-based nodal analysis technique. Each node, how much pressure it will tackle, how much deformation will happen. Those things can be simulated by using the Sugar. All other softwares which I have shown above are costlier, payable softwares, whereas Sugar is an open source software which we can do it. And the last thing which I am going to explain you is the COMSOL. The COMSOL sees this MEMS sensor in terms of physics. Either it may be a process simulation, or it may be a system level simulation, or it may be a linear or non-linear analysis, anything. It views anything. Why I am calling anything means, suppose you have a MEMS sensor. That structure you have been defined. The structure, for defined structure, how much mechanical strength it will be having, whether it will be rigid or whether it will be flexible. That can be defined by using solid mechanic physics. Whether structure will get reacted with any other chemical, then it is going to be a chemical reactive, electrochemical. If it is producing some amount of current, then it is electrochemical physics. Suppose the same structure, if you define it, how much it will be producing the resistance. Suppose if it is a semiconductor device, how much resistance it will produce, piezo resistor. Then that structure is defined by using semiconductor physics. So it sees everything. For example, a wood is an insulator. So a wood can be defined as a solid mechanics. If you want to study the structure, if you want to study the mechanical property of that wood. If you want to study as an insulator, the same wood is defined in terms of semiconductor physics. It will act as a semiconductor component, a wood itself, what I am talking. Okay, so the COMSOL is a multi-physics. Anything it views as a physics. Okay, to solve a problem. Okay, to solve a problem, any problem which you are taking, either it may be a research problem or it may be a real-time problem. It sees anything as a physics. Okay, so there is a comparison table. What are the features of this COMSOL and this counterware and IntelliSuite? some of the external softwares which can be interfaced with consoles are mimics. There is a software which is used in hospitals and all. CT scan and other MRI images are taken, and from that the structure of that organ or any other thing have been taken, and it is converted into STL file that can be imported into COMSOL for further study. Okay. For example, if you want, for accident people, if you want to produce a plate, if you want to place a plate in a fractured leg, the CT image of that patients have been taken into the mimics and it has been processed. Then the corresponding CAD structure have been produced. Then it has been incorporated in the COMSOL to study, to keep this corresponding plate inside that structure, whether what is the size, what is the thickness, and how much rupture it will be taking, what kind of material we can keep. Those studies we can study. Okay, like that mimics. If you want to import Excel data, those things can be imported. There are so many softwares which can be integrated with COMSOL. With other also, ANSYS also integrating with SolidWorks and other softwares and supported formats. And there are user-friendly multi-physics modeling and simulation integration. So the COMSOL multi-physics is the combination of several physics phenomena, what I told already, which is describing that particular process. So these physics are defined based on the law of physics. That law of physics will defined using differential equation. Okay, so by using this differential equation, we can study the behavior of that sensor or behavior of that structure. Either it may be a mechanical study, or it may be electrical study, or it may be electronic study, anything. So in COMSOL multiphysics, first what the steps involved is, first we have to define the model, and that model geometry we have to define. For defining that model, we need the software, or directly we can define in software, COMSOL itself. We can draw that geometry, or we can import it. And next, after defining geometry, we have to select material. Then we can, that material either can be defined in software itself, or you can import it from other softwares, or whether you can have it as a file, you can import it. Then you have to apply the physics, which physics you want to study. Then define the boundary condition equations and the values. Then mesh. Then run the result, run the COMSOL model. Then if you have any problem, optimize the values, compare it with desired solution. If you have any problem, go to the above steps, and when you get a better result, you can stop the simulation and you can get the result. Okay. Next. Next slide. So what are the physics available in the COMSOL? So what are the modules which is available in the COMSOL? AC/DC module, RF module, wave optics module, ray optics module, plasma module, semiconductor module, MEMS module. Okay, these are all the for electrical, for mechanical, structural, nonlinear structural, geomechanics. then fatigue, multi-body dynamics, then rotor dynamics, acoustic modules. These are all for mechanical study. And for fluid, computational fluid, mixture, surface flow, civil engineering, people are using most probably here. Pipe flow, even our biomedical people, for example, the electrical modules are used only by the either electrical or the electronics people. That mechanical people will be using structural and non-linear structural, those modules. And civil people will be using computational fluid dynamics and the other mixture, pipe flow and other thing. Chemical people will be using chemical reaction and other thing. Then material physics people, chemistry, science and humanity people will be using optimization technique and material libraries and particle tracing, those modules. But when you come to biomedical, that is the when I talk to students and everyone, it is a field of interdiscipline. We use all the modules because when you go to the blood flow in human body, that can be designed by using the Kamsal multiphysics. For example, suppose if you have any block in any artery or any venous veins, in any veins or arteries, you can simulate it using the computational fluid dynamics. If there is any block, you can get the block size using the CT scan, and you can go for the angiogram, angioplasty, to remove that block in the vein or in the artery. Okay, for that, computational fluid dynamics is used. Kamsal multiphysics computational fluid dynamics is used in real time. How much stress will be there? We'll be studying, or how much rupture will be happen during that angioplasty or angiogram. So in biomedical, we use all the modules. That depends upon what kind of system or what kind of target we are going to achieve, what kind of task. Yes, what kind of task. Because when you are talking about the blood flow itself, when you are using angioplasty, how much temperature will be produced? That can be studied. Okay, so thermal stress and other thing which comes under your mechanical. Same way, how much rupture will take place, that comes under stress and other thing. Okay, so the same blood flow we can see how much surface flow. Suppose if you are placing a stent in that vein or artery, the flow can be Newtonian flow or laminar flow can be studied. Okay, so biomedical field, Kamsal multiphysics plays a vital role because we have different tasks for a same organ itself. Okay, because each organ is having, for example, if you want to define electrical activity of your heart, then you can go for the electrical modules of your Kamsal. If you want to study about the pumping action of your heart, then you have to go for the structural mechanics of your Kamsal module. Suppose the blood flow, if you want to study of the same heart, then you have to go for computational fluid dynamics. Then chemical reaction, suppose if you are delivering any drug or any oxygen or something, how much reaction it takes place with your valve, your muscle of your heart. That you can go with the chemical reaction, or if you are having the drug delivery, what kind of chemical reaction that takes place in the same heart. That we go for chemical modules. Okay, so for biomedical field, the COMSOL multiphysics plays a vital role. So now I go with this introduction, how to simulate MEMS. So I will show you a live demo of the software. I will share the COMSOL multiphysics software for you. Okay. Sorry, Madam, Sudha Madam, anyone is there?
Tell me,
Is
sir.
it visible? My screen is visible. Either the COMSOL software is visible.
Yes, sir. Yes, sir. Yes, sir.
COMSOL is visible. Okay. So in the COMSOL software, which we are going to use for designing a MEMS sensor. Okay. So if you want to design any kind of system or any kind of device using COMSOL, first you have to double click it, it will display, it will pop up the window like this. Here on the top, if you see, we'll be having home, definitions, geometry, materials, physics, mesh, study and results, and developer. Here we need to concentrate on the geometry, materials, physics, mesh, and study and result. The developer is required to, if you want to make it into a separate app or some other thing, you want to produce a result for that purpose. It's not that much required. Similar way, definitions and we can define the equations. For that purpose, we need the definitions. But the primary menu, important menu in the COMSOL is geometry, materials, physics, mesh and study and result. So here we have two menus below, blank menu as well as model wizard. If you select a model wizard, then you can select already available model. If you select a blank model, then it will appears here blank model. Okay. So like opening already available document and opening a empty document. That is the thing. Now I have selected a empty document. First, for anything, as I told, we have to define the geometry. Okay. For defining the geometry, we have to know whether first we are going to do one-dimensional simulation, two-dimensional simulation, or three-dimensional simulation. So for that, you right-click the untitled.mph. The normal extension of your COMSOL file is .mph. Okay, anything you want to save it with an extension of .mph. That is the primary file of your simulation. MPH refers multi-physics. Okay, so that is the thing they are symbolically representing .mph. If you see add component, which component you want to select, either 3D or 2D or 2D axis symmetric, 1D or 0D. Okay. Some people may not be aware that what is 0D. 0D is nothing but a point. Okay, a single dot-like structure that can be defined. Okay. So suppose I want to select a 2D, then I select add component 2D. Now the component will be get added. Okay. Now the geometry is there. Here, whatever the geometry, if you want, you can draw it. For that, the properties you have to define, whether it is in meter or milli or kilometer or something, whatever the uh, that SI unit you want to define, that you can define Armstrong, nanometer, micrometer, millimeter, centimeter. That definition of that SI unit and angular degree, radiant or in degree, that you have to define, and tolerance. This you don't bother about it. Those two are very much important. Now, after that, what geometry if you are going to import? Okay, if you want to import a circle or ellipse, if you right click the geometry, okay, if you go to geometry, you can have the so many shapes which you want to simulate. Okay, for example, in the top also you will be having a geometry. If you click it, there you will be displayed with quadratic equation, cubic and points, rectangle. In rectangle, you'll be having the subtopic, square, and other thing. Whichever you want, you can select it, and that will be added to your component. For example, if I add a rectangle, okay, I have added. So I have selected, that will be added here. This rectangle have been created. Okay. Suppose I want to change it in millimeter, it will be in millimeter. So built on will be provided. So like this, you can add it any kind of structure, and if you want to change it a circle into a semicircle or anything, everything you will be having definition, and you will be having go to geometry. That line you will be having cubic, point, quadratic equation. That's solid. You can transform it into a different array. You can generate it for one point, and if you want similar that 100 points, then you can go for array, making it an array. Okay. So in geometry, you can use it any kind of geometry if you want, that can be selected. Here I delete it now. It's because I cannot. The time will be very less. So I go for importing. Suppose if you want to import, okay, it is in SolidWorks. You have done it in ANSYS or in some other 3D softwares which is having .stl format. Everything can be imported in the console. So there are different formats. For example, go to import. I right click the geometry and went to import. Here, if you see the label is import, and in source we have any importable file. Okay, either COMSOL multiphysics, one COMSOL you may have one geometry. The same geometry, if you want to incorporate for this simulation also, can go for only the COMSOL multiphysics file. Mesh files in ANSYS and all, you will be producing mesh files. Okay, that is data object and some other thing you'll be having. And ECAD files, electronic CAD, in TCAD, IntelliSuite, Counterware, you'll be producing so many formats. Everything will be having .stl. Those STL format can be incorporated here. Similar way, SolidWorks files .spdldr. Okay, those files also can be imported. Okay, so here I select. I don't know what kind of file I'm going to import, so I select any importable file. Go to browse. See, suppose I have any model. Just a minute. Just a minute, please. Okay. Because I'm not having 2D geometry. Instead of that, I will delete it because the geometry which I have selected is 2D. So here I will select a 3D geometry so that I can import it. I am not having any 2D geometry. That's why it is not showing. So yes, now you see there are so many files which you are seeing here. I can show you. Yes. So here I am having a heart wall. So it is in the ANSYS format which I have been designed. So I have imported. So it is getting importing. Okay, if you see here in the down right hand corner, there is a cross, red cross is available, which shows that it is importing the geometry which I have been selected. Okay. Empty geometry. Okay. So now I have imported a 3D CAD model of the eye. Okay. This is my research where I am designing a eye model in which I am going to place a photovoltaic cell in the retina. Okay. So now I have designed only the CAD model, but photovoltaic cell separately I am designing. So which will be placed at this point. Okay. This is the point where the photovoltaic cell, the retinal region, how the behavior of that retina, artificial retina will be there. So that is the concept of the artificial retina research which we are doing. So now here multi-physics is involved. What kind of multi-physics it's involved means, suppose I place any external body at this point, what kind of mechanical stress that will be provided to the muscle. So this I have defined some structure. Okay, this is the geometry. But this geometry, which I have shown, whether it is a wood or it is a plastic or it is going to be a any other material, any semiconductor material, that you have to select it. For that, you have to go to material. Okay, in material, already materials are available. Add material means the material which is already available in the library, you can add it. Or if you want to define it, you can define it by using user defined material. Okay, so if you see here in the right hand side, here material, add material is here. Similarly, at the top also we are having that materials. Similar way in right hand side, if you see the add materials, here you can go and see in bio heat. Okay, there are so many biological components or biological tissues have been defined. Okay, so bone, fat, liver, lungs, muscle, myocardium, prostate, renal cortex, skin, spleen. So you can select any of these material. Suppose I am placing a material, for example, one of the photovoltaic cell inside this I means I have to go to semiconductor. In semiconductor, I have to select which kind of material I am using, either silicon-based photovoltaic cell, germanium-based photovoltaic cell, or gallium arsenide-based photovoltaic cell. That material should be selected. Okay, so now for this I have to select the muzzle. So I define the muzzle. So that muzzle will be added here. See, under material below geometry, the material have been added. So muzzle have been added. This muzzle will be having certain property. Normally, the biological components are defined by using heat capacity, that is at constant pressure. What is the heat capacity? Density and thermal conductivity. Okay, if you want to define any other parameter of your material which I have not defined in basic, so these are the basic parameters of your material, of the muzzle. Okay, if you want to define any other material basic property, for example, see the absorption coefficient of the muzzle. So above the material constant, if you see material type, if you see there is material properties, in that you select basic property, there you go, what are the properties you require, that you can select it. Absorption coefficient means if you add it, if you select it, that will be added here. So see, I have selected absorption coefficient by selecting D plus. So in the material content, if you see absorption coefficient have been appeared, it has been added. And now the values, if you want to enter whatever the values, for example, I have been absorption coefficient 4, enter it, and the value will be defined. So this is the way how you want to define the material properties. You will be having material properties in these settings and properties. You will be having the corresponding properties. We can select it. Anything, permeability, permittivity, relative permittivity of the muzzle, relative permeability, resistivity of the muzzle, anything. Suppose if you are, want to study, for me, the resistivity and all required for the muzzle. In which way means, suppose the photovoltaic cell generating current is passed to the muzzle, that will be get conductive. Now, how much amount of resistance will be provided that muzzle? That I have to define by using the resistive. And relative permeability, relative permittivity, when you are using the optical, the light tissue interaction and all, you have to define. You want to define specific heat, relative permeability, relative permittivity and all. Okay. Even in eye also, the amount of light which entering into the eye reaching the retina, you require relative permittivity, relative permeability, other things in the different layers. Then only you can study. Okay. One good study of the Council multiphysics by using the eye is, suppose vitreous humors, aqueous humor have been damaged. It has been removed due to certain reasons. That vacant place will be filled with silicon oil nowadays by using the. Now, if you place a silicon oil in the place of aqueous humor, what will be the behavior of your eye? That can be studied. That can be studied by using the COMSOL multiplication. This behavior of that silicon oil varies with respect to different people, different patients, because each person will not have same physiological behavior of your eye. Okay. Now, after defining the muscle material, that is material, then you have to define your physics. What kind of physics you want to study? Suppose if you want to study the bio heat, okay, produced by that sensor which is placed inside that muscle, go to add physics. Then here if you see different physics as shown in the slide, the last slide of the PPT, I have shown the different physics modules which is available in the COMSOL. Chemical spectrochemistry. Suppose if you are designing a that is hello, madam, anybody? Yes. Okay, ma'am. I am getting that the internet connectivity is disabled. That's right.
No, sir.
Let's
Keep on
change.
continue, sir.
Okay. So we have to select the physics. Suppose if you are using if you are designing a glucose sensor, then electrochemistry will be playing a vital role. There we have to select electrochemistry. Now, for example, I am studying about the heat transfer. Then go to heat transfer. There, if you see a bioheat. Okay. So this bioheat transfer, if you select it, then we can study the heat transfer between the different muscles. Okay, different layers in the eye. We can also study it. Okay, so see here what are the things: physical model, heat transfer in biological tissue. Okay, other physical study also involved with this heat transfer, bioheat transfer, surface to surface radiation. That is outer eye. What will be the radiation? Radiation in participating media, whether inside the human body. Suppose for eye transplantation, you have to take the eye outside and you have to keep it in some other box. There, the media will be different. So, what will be the behavior of that eye inside that box, preserving box? Okay, so that media, radiation in participating media, okay, isothermal domain, heat transfer in alloys, porous media, there are different. Now here we have selected the bioheat. Now, in bioheat, the biological tissue and its parameter. Now, if you select it, in the right hand side, if you see, these are all the parameters. What are the parameter? First, for bioheat, we require the thermal conductivity. For thermal conductivity, if you want to use the parameter which is defined in the material, for example, here muscle we have selected. So thermal conductivity here we have defined. Okay, for muscle it is 0.9. For whether the same thermal conductivity is we are using means it's okay. We can select it that from material. Okay, from material we can use it. Otherwise, if you want to define, for example, I cannot use same thermal conductivity for different layers of the eye. We are having sclera, we are having lens, we are having retina, we are having optical disc region. There are so many regions available in the eye. So we cannot use the same thermal conductivity. By selecting different region. So aqueous humans means I can give different thermal conductivity. So I can add different physics and different values. Or otherwise, if you want to use it from material means you will take from the already in second step where we have defined the material. In that material, we have defined the thermal conductivity. That value will be taken. Okay. So in physics, we have to define the values. Certain things which we have not included here, uh, which we want to simulate. For example, translation motion is not there means you can add it, right click it, add it, and add that physics and corresponding the translation physics values. Okay, so if you don't want, you can remove it. Okay, similar way, initial value, thermal insulations. So what are the physics parameters which I have not included? Here see heat flux which can be included, thermal contact. Okay, there are so many other physics which we need to simulate, radiations, diffuse surface, which surface, suppose as I told the drug delivery, when you are using for if you want to study the eye drops, okay, so what is the diffusion level in the lens, in sclera and other point, you have to select the diffusion surface. Okay, so there are so many other physics are available, inflow, outflow. In vein and for example, in arteries and vein, when blood flows, you have to define what is the inflow point and what is the outflow point. In spirometer also, we have to define inflow and outflow, that heat and the temperature, heat sources, everything we can define by using right clicking. So by right clicking, we can identify what are all the physics available. Okay, the values if you want to define, these are all the equation expressions which default you will be having in the COMSOL multiphysics itself. If you are using biotransfer means automatically the heat source equation, total heat source equation, metabolic heat source, and those equations will be already defined. Okay, by using these equations only, you will be having your results. Okay, if you want any additional equation, that can be defined in the top menu, global definition. Below that we have the parameter. Here you can right click it, then you can add it. If you want, you can add the parameter here itself. Okay, whatever you want additional parameters, you can add the parameters here itself. That is by variable, by function. Okay, analytic interpolation, piecewise. These are all the equations which we can define additionally for our simulations. Okay. Then mesh we have to include. So add a mesh. So there are different pre-processing and post-processing, but we can go for simple mesh. This mesh only will define the finite element analysis. Okay, so that mesh is defining how much points normal or physiological physics-based control mesh or user-defined control mesh, and everything will be defined. Whether fine, coarse, extra coarse, extremely coarse, that mesh based on that, because based on the mesh values only, you will be getting the accurate. Okay, extra fine is better normally, if you have an extra fine, very small changes, okay, between a between minute point changes, minute value changes, that can be identified with your equation. This mesh will utilize the iteration. Okay, mesh will be utilized in the number of iteration based on your whether it is normal mesh or it is a fine or finer. Based on that only, you will be having number of iteration for your differential equations. Okay, it will define. Okay, either 200 times or 300 times. That because one iteration value will be taken to the next iteration. Okay, that is the finite element. Okay, then after defining here, you have to go for defining your result. Okay, so you have to add a result after adding. Either you need a 3D plot or 2D plot, that you have to go to result and you have to add it. Okay, so in result, you make it, suppose 1D plot means go for 1D plot, it will be added. That 1D plot, what parameter you are going to plot, okay, that you have to select it here only. Okay, automatic data set, either from user defined x-axis or any other variable which you are defining in parameters. Suppose any variable you have defined that, and remaining result you have to take it from the simulation means that you have to define for which two parameter you want to plot it. Okay, that you have to select it here. Manual spacing, another thing, upper right, those things, how much plot you have to plot it. Okay, so here we will be having the surface plotting, 2D plotting, 3D plotting, another thing. So we have to define the geometry, then we have to define the material, which material we are using. In material, we have to define the corresponding material properties. Okay, even user defined properties also there. If you want, you can define user defined. If you are not interested in defining in material, you want to define in global variables means you can define here itself as a variable in expression or as a variable, you can parameters, everything you can define it. Then you can utilize it inside the physics itself. Okay, here. Then select the corresponding physics, then mesh it. In meshing, you have to select the fine or extra fine, extremely fine. Then finally, in result, you have to select either 1D plot or 2D plot or 3D plot. Okay, this is the general procedure for designing any design, any task of your target. Okay, so now I'll share you already. This is my research, which is not fully simulated. Okay, so I don't want to. These are the steps which involved in the COMSOL multiphysics. Now I want to share a glucose sensor model which is available in the COMSOL multiphysics itself. Okay. So this is the model which is available in the COMSOL multiphysics. Here they had defined a microstrip as a rectangle, and these are all the electrodes. The dot which is available, black dots, points, have been defined as electrodes. Okay, those electrodes are the sensing electrode, the concentration of your glucose. So this is structure. Now here we don't define any system. Okay, that's why I told the COMSOL multiphysics is having both system level definition or device level definition. Here, this project or this model is defining the device level, which is having the strip, that glucose strip which we are defining. That strip is having the electrodes. that electrodes are the points which we are defined. Okay, when it is reacted with the blood, it will generate some amount of current. That current will be measured and it will be plotted how it will be behaving. That is the this model. Okay, glucose model. Here we are defined a rectangular structure in which points defines the electrodes and array of electrodes. This 4 will act as a array of electrodes. So we have combined and we have built. After defining geometry, every time you have to build all the objects, then only the point, rectangle, whatever the structure we are defining, it will be get builded. Okay. Now after that, there is no material here we have defined, that is optional. Instead of that, we have selected the electroanalysis. There we have defined the transport properties and initial values. Surface electrode, see the surface electrode is the middle and the reaction electrode is on the both side. Okay, counter electrodes are defined on either side of that central electrodes. Okay, so here it's use a stoichiometric coefficient, that corresponding equation. So electroanalysis material volume equation, that equations here we are having. Okay, so those values, if you want changes, and corresponding equation is here defined. Then mesh. Okay, the size of the mesh here we have selected. Okay, general physics extra fine. Okay, so extra fine will give you a better result, as I told. Okay, finally, what kind of steady? Okay, in the steady we are using simple stationary. Okay, this compute stationary steady solutions will be given, that corresponding variable. What are the variable that you want to study? Here you have to select it. Okay, so in steady, whatever you are selecting, that can be utilized for the result also. Okay, there are different kind of studies available. If you right click it, so which I have left out. Okay, so parametric sweep, functional sweep, material sweep, combined solution, parameter optimization, stationary. Here we are going for stationary study. Normally, most of the people, any kind of simulation in comes up, will go with stationary and time dependent simulation. Okay, so both time dependent and stationary studies plays a vital role. Most of the simulations in comes are multiphysics. Okay, here in glucose sensor they have selected stationary study. Okay, so that stationary study already have been selected, so I delete this. So stationary study is there, and what are the components that I want to study? That you have to select here. Okay. So here it has been selected glucose. Okay, component 1.c ferro. These are all the in equations what we have seen here in electrolysis transport. Here you will be having those parameters. Okay, those parameters have been selected here: concentration, glucose concentration, and reaction with ferroelectrode. This electrode. So how much reaction it is producing? Okay, with respect to your blood concentration. Okay, this counter electrode parameter that is selected. So this will be simulated. Now in studies only, when you come to study, here you will be having compute. When you compute it, the sensor you have designed will generate a result. So now it is computing the right hand lower corner. It takes yes. Now the computation have been over. What are the steady? Okay, here they have studied so many studies, but they have plotted only one plot, the concentration. The concentration, if you see the right hand side, the blue color indicates the lowest concentration and the red indicates the highest concentration, 1.8. That 1.8 is available at the end of the strip where your blood is available. That how much amount of that is glucose level, okay, which is interacting with your counter electrode at both point, okay, which provides amount of current, okay. So this is the behavior how we are simulating MEMS sensor by using the COMSOL software. So this indicates the level of glucose. So similar way in real time also the same strip when you are using, which will produce the current ranges that interacts with your blood also. So this is the graph. So 1D graph which has been drawn between the glucose as well as the average current, the linear. Okay, see this linear graph, okay, which it has been produced. It shows the relation between the glucose as well as the average current produced by that MEMS sensor. Okay, so now I have shown you how you have to define a geometry, how you have to define a material, how you have to define a physics and corresponding equation, meshing, as well as the study, and then producing the result using the COMSOL multiphysics. Okay, but because we cannot take any specific example and showing you designing of MEMS, because MEMS having its different level of multiphysics. Okay, this here we have shown only the electrophysics analysis of the MEMS. The same the glucose sensor can be studied with semiconductor physics. How much amount of the electron flow is available? Then only we can identify the average current. Okay, so when you know only the amount of current flowing which is coming from your glucose sensor, then we can have the signal processing unit. We can amplify it. Then we can identify this much amount of glucose is available, and that is given to your microcontroller. Then it is displayed on your display of your glucose meter. Okay, so here only the interaction between the sample and the MEMS sensor physics, that is electrophysics, have been electroanalysis, but semiconductor physics is there. That we have not studied. That if you want, you go to semiconductor module, then add the semiconductor, then you have to define the ferroelectric property, semiconductor property, then you have to give the internal external source of electrical signal. Okay, so each module has its own physics. Okay, so same glucose sensor can be studied with solid mechanism, because when you insert or when you attach the sensor with your glucometer, sometimes it may get broken. So how much flexibility it is having, or it should not damage your sensor element which is available in the glucometer. Okay, so what is the mechanical or what is the friction that happens when you are attaching the same glucose sensor with the sensor available in the glucometer? So that study between the glucose portable uh, portable instrument and the MEMS sensor that we can study by using the solid mechanics. Okay, here I have shown you only electrochemical perspective of your COMSOL multiphysics MEMS module. Okay, the same MEMS module can be seen in a different physics like solid mechanics or semiconductor mechanics or AC DC electrical. Suppose if you are some sensor which has been fabricated on the motor itself, certain stepper motor which Turing tooth some sensor available, dental sensor Turing your teeth also. Their stepper motor is run based on your MEMS sensor. So there AC DC module plays a vital role. Okay, so this is the way. First we have to define the geometry, define the component, whether it is 1D component, 2D component or 3D component. Later you have to define the geometry, then you have to define the material, then you have to define the physics, then you have to define the mesh and study what kind of study you are going to do. Then from the study, type of study only, you will be getting the data and you have to plot it. Okay. Thank you. Madam. Thank you for this opportunity. I have given some basic information about the COMSOL and how to define, how to simulate the MEMS sensor in a multi-physics environment. Is there any query? Please ask, because I am doing certain modules only, not all the modules. If you have any basic doubts and anything, you can ask me. Madam, you can take over, madam. Can I? Sudha, madam?
Yes, sir. And participants,
Yes, madam.
do you have any queries?
Madam, is it useful for you? How it is, madam?
Sir, it is very informative, sir.
Yes, madam. Yes, madam.
Participants, any queries?
Even you can put it in chat box also. I can read it. I can give you answer.
So this software is open source, or I have to?
Oh, it is a very costly software, which I have attended COMSOL conference. They have given at that time open source for 1 month or 3 months license. So I am changing the date and I am placing it sometimes. If you want to publish without license, it is not possible. The software, they will lock your paper and other thing. If you want to
trial version, sir, we cannot do trial version.
You cannot have all the modules, madam. All kind of studies we cannot do it. You will be struggling in simulating certain physics that may not be active. They may be disabled. They will not make you everything.
What about the cost of the software?
It depends the module, madam. Suppose if you take about AC/DC module itself, the first cost of the software is 1.5 lakhs. Okay, only software, not modules. Then for individual module, AC/DC means in AC/DC you will be having sub-modules. Okay, each sub-modules will be having some 60,000. So for example, AC/DC available means you will be having some 4 sub-modules or 6 sub-modules. So for AC/DC module itself, you want to pay some 3 lakhs rupees for floating license. So similar that you will be having more than 10 to 12 modules, main modules available. In that, you will be having sub modules. When I have been inquiring that for my college, the total cost comes around from 50 lakhs when you talk about all the modules with all sub modules.
Okay, sir.
But it's not required all the modules, madam. That requires depending upon our target, our simulation. Whether we need opticals. Suppose, for example, if I am doing photovoltaic cell modeling means for me, I need only semiconductor module. Or at the maximum, I can go for wave optics or ray optics. More than that, I don't require any other module for photovoltaic or semiconductor-based modeling. Suppose if you are going for implantable devices, that is like heart valve, or suppose if you are going for a plate which is placed inside the bone, or any other stent designing, angiographic balloon designing, these and all you can go for with solid mechanic modules and computation fluid dynamics modules. It does not require any MEMS modules or any other modules.
Okay, so one question from Sudarvali ma'am in chat box. How about
Yes.
the usability as prototypes, sir?
Prototype. You cannot do any prototype by using this software, but you can generate a structure which is required for your prototype. You can study those structure properties, those structure behavior, those structure behavior and properties you can study in COMSOL multiphysics. Okay, that multiphysics, as I told, suppose if you are placing a heart valve inside a cardio, your heart, then you can study tissue interaction with your heart valve. Okay, tissue component interaction. Okay, there is a module available. That module you have to utilize it. Or if you want to study the solid mechanics, how much the suppose if you want to study the blood flow, what is the pressure on the opening side, what is the pressure on the closing side, that you can study by using the that is laminar flow, or that is there are different kind of flow techniques available. Using that biomechanics flow techniques, you can study. Or if you want to study that same heart valve, how much rupture it is producing, okay, that you can tissue interaction, okay, that component tissue interaction can be studied by using the COMSOL multiphysics. This can also be studied by using ANSYS also. Okay, ANSYS is also similar to your COMSOL multiphysics, but minute values, that is 0.001, like that, at biological level, COMSOL multiphysics is having better accuracy than your ANSYS product of your multiphysics. Both are using only finite element analysis technique, meshing technique for producing the result. But COMSOL is having multiphysics. As I told, in ANSYS, you cannot go for a semiconductor physics. But in COMSOL, you have a semiconductor physics as well as your solid mechanics. Both can be interfaced. What I have told, for my eye, I have a solid mechanics. When I place an external component inside my eye, that muscle, whether it will be accepting it or not, that external component, okay, that can be studied by using the solid mechanics, ANSYS. But the photovoltaic cell behavior cannot be studied in your ANSYS, because optic wave and ray optics combined with the solid mechanics can be studied only in COMSOL multiphysics.
Okay, sir.
That cannot be done in your ANSYS.
Okay, sir. Thank you, sir.
Thank you, Sudhari, madam. Any other questions?
Thank you, sir. Thank you.
Thank you.
Ma'am, Shubha ma'am?
Yes, ma'am. Am I audible, ma'am?
Yes, ma'am.
It's my privilege to propose a vote of thanks on this seminar. On behalf of the Department of Biomedical Engineering, PSNA College of Engineering and Technology, I would like to thank our today's program guest speaker, Mr. T. Alavandar, Assistant Professor, Department of Biomedical Engineering, KPR Institute of Engineering and Technology, Coimbatore, who deliver the innovative idea on the topic biomem simulation using COMSOL multiphysics. I hope the session was very useful for the participants who are doing the ongoing projects in modeling and simulation of the MEM sensor. Thank you very much, sir, for sharing the demo session in the COMSOL multiphysics software. Thank you once again, sir.
Thank you. Thank you to everyone, participants, and everyone. Thank you.
Thank you, sir. Thank you, sir. Okay. Thank you, participants, for your patience hearing and listening. Feedback form, that link is posted in that chat box. Fill it the same. I will meet you in the next tomorrow's session at 9:30 a.m. Thank you. Thank you very much.
Thank you, participants.